Hello everyone. In yesterday's lecture, we have seen what is a Biot-Savart's law and the definition of your Biot-Savart's law, and which stated that the Biot-Savart's law, the magnetic field intensity which is produced for a particular point is proportional to your product of current and your differential length, and it is also proportional to sine of angle between the element and inversely proportional to the square of distance between these 2 points. Okay, so we have dealt with this in your previous sections. So in that relation, we'll just see what is a Biot-Savart's law and how we are going to find your magnetic field intensity for a straight conductor of your infinite length. Okay, so this is what the expression like yesterday what we have derived at, which is dH is nothing but your magnetic field intensity, which is directly proportional to your current I and your differential length into your unit vector divided by 4 pi r12 the whole square, and a12 is nothing but your unit vector, which I can derive it as r vector upon magnitude of your r vector, and the same thing can be extended in a form of an integration as well, and this equation is called as an integral form of your Biot-Savart's law. And these are the different current distribution for your line current, surface current and your volume current. So a line current which is represented for a particular line can be given as I dl ar upon 4 by r square, whereas for your surface it is dealt for your differential surface area with your current density K is being assumed, and if the same thing can be extended for a volume for a given conductor of J, which is usually measured in your ampere per meter square, then your differential volume I into dl can be expressed as J into dV. Okay, so hence the Biot-Savart's law can also be expressed for a surface current as well as your volume current. So this form of your Biot-Savart law is also called as Ampere law for a current element. So this is the expression what we have got, and let us apply this expression to determine a magnetic field due to a straight current carrying conductor which is of a finite length of AB. Okay, so let us consider this expression where let us consider a conductor which is of finite length and it is placed in your z-axis as shown in your diagram. So it carries a current I in this direction. So the distance which is perpendicular from a point P from your z-axis is your rho. So this rho can be anonymously even used as a r. Okay, so r is nothing but your rho. Okay, so the conductor is placed such that one end of the conductor is at z equal to say a, another end of the conductor is at the other distance say z equal to b. Okay, so considering this differential length dl along your z-axis, I can now find what is my dl vector. So this dl vector I can write it as your dz for this entire, okay, so this is your dz into my az vector for that particular point. Okay, so the unit vector in this direction for a point P I can just express as r12 for your first and 2 points. Say let this point A be a 1 point and B be your second point. So I can just express your A r12 is equal to, as usual as we have seen this, as r12. Okay, so same thing here. So r is nothing but r12 I can just express as r12 upon r12 square. So this r is your unit vector. So I can just write it as minus z az plus rho into a rho. So this again I can even call it as r into ar. So what we have got from here is, so this particular point of B, okay, So I have 0 comma 0 comma z, whereas this particular point of P I have your row along, so it is your 0 comma row comma 0, okay, which is in your xy plane. So with that consideration, I'll be having an expression of r vector is equal to minus az plus rho into a rho. So magnitude of this I'll be getting it as root of z squared plus my rho squared. So again my unit vector, as I have told you, r divided by r. So r I have minus z a z plus rho a rho divided by root of z squared plus rho squared. Okay. So now combining these two terms, and this h is nothing but a formula of my Biot-Savart's law for finding your magnetic field. So I'll be just having I dl ar divided by 4 pi r squared. So I dl into ar is nothing but your distance vector from my point where I have to find. Okay, so this r is nothing but what I have got, I into dl. dl is nothing along but your dz, what I have arrived at. Okay, into your ar vector is along your z axis, so I'll be having my az into integration of this r vector was z minus z az plus rho into a rho, okay, divided by r cube is nothing but I'll be applying r divided by magnitude of r squared, so it gets multiplied and you get r cube. Okay, so root of, you will have root of z squared plus rho squared into z squared plus rho squared, which gives me z squared plus rho squared into 3 by whole power 3 by 2. Okay, so now at last what we have to find? We have to find the cross product of my z along axis along with your distance vector where I have to find your magnetic field intensity. So that will give me dlr equal to, so this a rho, a phi, az, and this is dx, dy, dz. I don't have a dx component, I don't have my dy component. So these both are 0 and I'll have dz. Okay. So next is again x, y, z, z. So x component is again rho and z component is again minus z. So which will give me finally I rho z. I have to substitute again back in this expression. This expression I have to substitute. So I'll be getting I rho z dz divided by 4 pi z squared plus rho squared whole power 3 by 2. So in the last infinitely long conductor, we have just considered your z vector, z is equal to r into tan alpha, or else we can just go for finding a figure and have a relationship of your alpha and your z. Okay, so in that we'll have with your trigonometric figure. So in the previous figure, I can just find this. Okay, so which has a trigonometric rule, you have an alpha and you have your rho. So what will be my tan value? Tan will be, tan alpha is equal to rho divided by z. Okay, so z I'll be having z rho divided by tan alpha. 1 by tan alpha is my cot, so z is equal to rho cot alpha. Okay, so differentiating this, I'll be having dz equal to, differentiation of cot is cosecant, so minus rho cosecant alpha into d alpha. So substituting all this in your previous expression, I'll just have this value of, okay, so I have to substitute this. I have next I by 1 I by 4 pi, I have taken it commonly outside, and I have value of rho. Okay, so rho is nothing but z into tan alpha. Again I'll be substituting, so this value of dz I have to substitute. So dz is nothing but rho cosecant alpha d alpha, okay, divided by the value of z squared plus rho squared. Z squared again I have rho squared cot squared theta alpha plus rho squared. So taking this rho squared outside, I'll just have rho cube. So I'll have 1 divided by rho. Again 1 plus cot squared theta, I have to take it outside. Okay, 1 plus cot squared theta is your cosecant squared theta. So substituting all this value, I'll just have your rho squared gets cancelled out. So I'll have 1 by rho. Another again cosecant squared with cosecant cube, I'll have 1 by cosecant. So 1 by cosecant is by sine. Okay. So now then substituting the value of alpha 1 and alpha 2, I'll be just having alpha 1, alpha 2 minus alpha 1 into my A phi. Okay, so this is the general expression which is applicable for your filamentary conductor, which is of my finite length. Now in this case, like we have to keep substituting for your three cases. Let us consider for your case 1, when your point A, that is when your conductor is a semi-finite, it is not up to a finite length, it is of a semi-finite length, and your point A is at origin, 0 0 0, whereas your point B is at infinite. Okay, so now what happens, your alpha 1 becomes your 90 degree and alpha 2 becomes 0 degree. So I'll have my magnetic field intensity to be I divided by 4 pi rho into A phi. And what will be the next case? I'll be having your A at negative infinity and your B at positive infinity. So your alpha will be at 180 degree, okay, for your full 180 degree, and alpha 2 will be your 0. So same, you will have H is equal to I divided by 2 pi rho into A phi. Okay, so this is what is your basic expression for your magnetic field intensity, what we are deriving for your straight conductor, which is of your finite length. Okay, I hope you have understood this lecture. Thank you.